Yesterday, California's coastline sat at sea level. Today, it is towering 6 feet above the waves, leaving harbors stranded and marine life exposed on dry land. Scientists built their careers on the idea of gradual change, but this was instant, stretching for hundreds of miles. It is not just the speed that terrifies experts. A city block-sized, eerily geometric void has appeared beneath the coast, filled with a material unlike anything known on Earth. Could this be the warning sign of a disaster no one saw coming? Marin Govorchin has spent decades tracking every subtle motion along California's rugged edge. For most of that time, the coastline barely seemed to move at all. Tectonic plates grind past each other beneath the state, but their effects are measured in fractions of an inch each year, sometimes as little as 0, sometimes up to 4 millimeters. That's less than the width of a pencil tip, spread out over 12 months. In places like the Santa Barbara Basin or Long Beach, scientists have documented the land rising by a few millimeters per year, often tied to groundwater recharge or oil field operations. Even these so-called uplift hotspots are modest, and they unfold so slowly that only the most sensitive equipment can spot them. Govorcin's team at NASA's Jet Propulsion Laboratory relies on satellite radar and a dense web of GPS stations to watch for these changes. Each instrument is tuned to detect the smallest vertical shifts, down to the millimeter. Over the years, the data has painted a picture of a coastline in perpetual, gentle motion. Sometimes, the ground sinks as water is pumped from deep below. Other times, careful management of aquifers or oil fields nudges the land upward. But the pace is always glacial, never sudden. The largest changes on record, like the slow bulging at Portuguese Bend or the gradual rebound in Long Beach, accumulate over years, not hours. This slow dance between land and sea has shaped every scientific model and every coastal policy. The idea that California's shore could leap upward by feet in a single night runs counter to everything Marin Govorchin and his colleagues have ever measured. Their instruments are built for patience, not panic. For decades, the numbers have told a story of change at the edge of perception, steady, predictable, and, above all, slow. That's why, when the alarms finally sounded, no one was prepared for what came next. Dr. Eric Fielding arrived at the Jet Propulsion Lab before dawn, laptop in hand, determined to rule out the most basic explanation, a technical glitch. Every GPS station from Crescent City to San Diego had registered the same impossible leap, upward by as much as 6 feet, within a single night. Fielding's team started with the raw logs. They pulled minute-by-minute records from over 400 coastal GPS units, hunting for signs of interference, power failure, or sudden shifts in satellite geometry. Each station's data was compared against its nearest neighbors. No outliers, no drifting clocks, no evidence of spoofing or cyber attack. Next came the satellite radar. Sentinel-1 interferograms, processed through Jet Propulsion Lab's automated pipeline, showed the coastline's elevation change as a sharp, unbroken step, pixel after pixel, the same pattern repeated across hundreds of miles. Atmospheric corrections were checked and recalibrated. The results did not budge. Tide gauge records, downloaded from NOAA's observation network, told the same story from another angle. Water levels at every major harbor had dropped by nearly 2 meters in a matter of hours, far beyond the normal swing of tide or storm surge. Barometric pressure, wind, and storm data all failed to account for the change. Fielding's team ran through every known error source: multipath interference, data reference frame shifts, sensor drift, even the possibility of a coordinated equipment malfunction. Each possibility was tested and eliminated. The audit stretched through the night and into the next day, with outside experts from Scripps and USGS reviewing every step. By the end of the 48-hour review, the verdict was clear. The anomaly was real. The coastline had lifted. No technical error, no data corruption. just a raw, physical event with no precedent. For Fielding and his colleagues, the numbers were now undeniable. The only question left was what could possibly cause the land itself to rise so suddenly and so uniformly across such a vast stretch of California's edge. In the shadow of the Palos Verdes cliffs, the ground at Portuguese Bend has always seemed restless. In 1956, that restlessness turned to chaos. Decades-old homes perched above the Pacific began to twist and crack. Entire streets buckled. Residents woke to find their driveways split in two, lawns sloping where they had been flat the day before. By the end of that first year, nearly 70 feet of horizontal movement had torn through the neighborhood, dragging houses and gardens toward the sea. The land did not just slide, it warped and bulged, reshaping the coastline itself. One survivor, Margaret Alvarez, watched her childhood home dragged sideways over weeks. She recalled that it felt like the earth was breathing. You would go to bed and wake up to a new crack in the wall, a new tilt to the floor. They tried to keep living, but the ground would not let them forget what was happening underneath. The destruction did not come as a single violent jolt. Instead, it unfolded day after day, sometimes creeping, sometimes surging after heavy rains. Engineers measured movement at a centimeter per day, enough to shatter pipes, snap power lines, and force families to abandon everything. Over the next decade, the slide consumed more than 300 acres, with some spots rising or falling by several feet over months. Scientists traced the cause to a hidden layer of slippery clay, saturated by water and overloaded by new construction. But the true trigger lay buried deep below, out of sight and out of reach. For those who lived through it, the lesson was clear. The Earth holds secrets that no blueprint or boundary can contain. Mud Creek, perched on the remote Big Sur coast, delivered one of California's most shocking transformations in living memory. In May of 2017, a hillside that had been quietly creeping for decades finally let go. Overnight, more than 6 million tons of earth surged toward the Pacific, burying a quarter mile of Highway 1 and pushing the coastline out by nearly 15 acres. But what stunned geologists wasn't just the destruction, it was the way the land didn't simply slide down. The debris piled so deep and so fast that the new ground stood several stories higher than the old shoreline. Where waves had crashed against cliffs the day before, a raw, jagged plateau now overlooked the sea, lifted by the weight of the landslide itself. For marine biologist Lila Tron, the change was immediate and personal. She arrived at sunrise to find tide pools stranded high above the surf. Starfish, urchins, and abalone, once washed twice a day by salt water, now baked in the morning sun. Tran and her team rushed to rescue what they could, scrambling across unstable rock, gathering sea life into buckets as the ocean receded below. It felt like the world had flipped upside down, she later recalled. We weren't saving animals from oil or plastic. We were racing the clock against the land itself. Mud Creek forced scientists to confront a hard truth. Sometimes, the Earth moves with terrifying speed and finality. The event left behind a landscape so altered that maps had to be redrawn. It also left a question hanging in the salt air. What lies beneath the surface, powerful enough to reshape the coast in a single night? For researchers, that question demanded a new kind of investigation, one that would look deep below the ground for answers. Gravity meters lined up along the bluffs from Half Moon Bay to Ventura started reporting something no one had seen before. Unprecedented readings. Every reading pointed to a sudden loss of mass beneath the ground, a sharp gravity deficit stretching for miles, as if a chunk of Earth had quietly vanished overnight. Field technicians, still reeling from the coastline's leap, began hauling portable gravimeters and seismic sensors across the sand, double-checking the numbers. The figures did not budge. At each site, the instruments told the same story: less mass below their feet, and a pattern that traced a near-perfect line along the uplifted coast. Seismic crews, used to mapping oil fields and earthquake faults, fired up their trucks, and rolled out dense arrays of geophones. When the first active shots echoed through the ground, the returning signals painted an even stranger picture. Instead of the usual jumble of rock layers, the seismic profiles showed a hard-edged boundary, geometric void, clean and regular, cutting through the subsurface like it had been carved with a machine. Reflections bounced off the top of this empty space, but nothing came back from within. It was as if the earth itself had been hollowed out, leaving a gap the size of a city block, hidden just beneath the surface. The technicians huddled over laptops, tracing the void's outline and comparing notes. Gravity lows matched the seismic gaps almost exactly. The shape was not natural. No cave or sinkhole had ever looked like this. The mass deficit was too large, the edges too sharp. Whatever had caused the coastline to rise had also left behind a hole that defied every geological expectation. The field teams could only stare at the data, knowing they would need more than surface instruments to understand what they had found. At the United States Geological Survey Office in Menlo Park, Dr. Tom Parsons stared at seismic profiles and gravity maps spread across his desk. The void beneath the California coastline was not just a gap. It was a clean-edged chasm stretching the length of several city blocks, and nothing in the geological record could account for its shape or scale. Standard seismic reflection surveys run with trucks and geophones had traced sharp boundaries that cut through the earth in straight lines. Microgravity readings showed a loss of mass so large it was as if a piece of the planet had been scooped out in a single motion. Electrical resistivity cross-sections, generated by driving electrodes into the sand above the anomaly, revealed a block of material with properties that did not match any known sediment, rock, or groundwater signature. The numbers were consistent across every method. This was no sinkhole, no collapsed cave, no remnant of an old oil field. Parsons called in a team from Lawrence Berkeley Lab to discuss the next step, muon tomography. By tracking cosmic ray particles as they pass through the Earth, this technique could map the void in 3 dimensions, even hundreds of meters below the surface. Parsons explained that they were looking at something that defied every natural process they had ever studied. The symmetry, the size, the clean boundaries, none of it fit. If there was any chance this was a natural feature, muon imaging would tell them. But if it was not, they needed to know what was down there before anything else moved. Within days, plans were drawn to deploy muon detectors in old storm drains and maintenance tunnels along the coast. The hope was to capture a high-resolution image of the void and its mysterious fill. As the news spread, state and federal agencies demanded updates. City planners, insurance companies, and emergency managers wanted answers. How stable was the ground above, and what would happen if the void expanded? For Parsons and his colleagues, the evidence was now public. The coastline was no longer just a line on a map. It was a question hanging over millions of lives, and the tools to answer it were being rushed into place. At the state capitol, emergency meetings stretched into the night. The California Coastal Commission, caught between panic and protocol, demanded answers no one could give. A spokesperson addressed the press with a voice that barely hid the strain. Planning for the loss of a coastline we've always known requires imagination and uncomfortable compromise. Every agency scrambled to assess the damage. Insurance companies, faced with thousands of claims from harbors and beachfront homes suddenly stranded above the tide, froze all new policies pending investigation. The memory of $46 million spent to relocate the Gleason Beach Bridge hung over the room. A single mile of highway, rerouted after years of erosion, now seemed like a bargain compared to what lay ahead. City managers from San Francisco to Ventura called in engineers to inspect piers, storm drains, and water mains left dangling above the receding surf. Legal teams sifted through decades-old zoning maps, searching for loopholes to delay payouts. Harbor authorities watched as commercial fishing boats sat beached on what used to be the ocean floor, with no clear plan to restore access or compensate owners. The cost of rebuilding, if it was even possible, loomed over every discussion. State planners warned that entire neighborhoods might need to be relocated. The question of who would pay and how sparked bitter arguments in closed-door sessions. As the hours dragged on, one fact became clear: science wasn't keeping pace with the crisis. Without a definitive explanation, every scenario felt plausible, and every choice carried enormous risk. The Coastal Commission's official, staring out at a shoreline that no longer matched any map, summed up the mood. We need answers, and we need them now. Because if this isn't a fluke, if the ground can just move like this, then every plan we've made is out the window. Three explanations now haunt every meeting and late-night phone call among California's top scientists. Brute geology, a natural collapse or fault slip, so rare and violent it would rewrite textbooks. Teams pore over earthquake catalogs and landslide records, searching for any precedent. Nothing fits. No quake, not even the worst on the San Andreas, has ever produced a uniform uplift of this scale, let alone left a geometric void behind. Every seismic trace comes up empty. The ground rose, but without the violence, aftershocks, or shattered infrastructure that follow even moderate earthquakes. The second scenario points to human hands. Could tunneling or excavation, something on a scale far beyond any known project, have hollowed out the earth beneath the coast? Regulatory audits comb through thousands of permits, drilling records, and construction logs. No evidence of a mega project, no sign of unauthorized mining or secret tunnels. Oil field maps, groundwater recharge plans, and even military archives turn up nothing. The void's perfect geometry and unknown fill material defy every engineered structure on record. If this was built, it left no trace in the bureaucracy or the ground above until now. The last possibility chills even the most seasoned researchers. An unknown process, neither natural nor artificial, at work beneath California. Borehole samples drilled at the edge of the anomaly return fragments of a substance that baffles every lab. It conducts electricity like nothing in the local rock and resists every acid bath and spectrometer. The void's shape, the sudden uplift, the matching anomalies along distant fault lines, none of it fits the playbook. Each test only deepens the uncertainty. In closed-door sessions, experts debate whether to keep searching for a rational cause or accept that something beyond their experience has changed the ground beneath their feet. The coastline stands higher, but the foundation of scientific certainty has never felt so hollow. Today, the California coast stands transformed. Its foundations defy explanation. As scientists scramble to decode these unnatural voids, one fact remains: the ground beneath us is more unstable and more unknown than ever. Our cities, our lives rest on mysteries no instrument can yet solve. Sometimes, the scariest fault line is the one we never saw coming. 5 Filipino volcanoes are waking up at the exact same time. Scientists are shocked because this has never happened before in recorded history, and what's causing it could reshape the entire Pacific Ring of Fire. Picture Mount Mayon, Taal, Bulusan, Canlaon, and Hibok-Hibok, 5 deadly giants scattered across different islands, all suddenly showing signs of life within weeks of each other. Steam vents opening, ground swelling, earthquakes rattling communities that haven't felt tremors in decades. This isn't coincidence. This is a geological nightmare that has experts scrambling for answers. The Philippines sits on one of the most dangerous volcanic zones on Earth, but these 5 volcanoes have never synchronized their activity like this. Each one has its own deadly history. Taal killed 1,300 people in 1911. Mayon buried entire towns in 1814. And Hibok-Hibok wiped out 500 people in 1951. Now they're all stirring at once, suggesting something massive is happening deep beneath the islands. But here's what's terrifying scientists. Underground magma chambers that were thought to be separate might actually be connected by hidden pathways. If one erupts, it could trigger a domino effect that turns the entire archipelago into a volcanic war zone. Are we watching the countdown to the Philippines' worst natural disaster, or has it already begun? April 2025. The FIVO-LCS Command Center in Quezon City is already running on high alert when the first wave of seismic alarms hits before dawn. At 5:51 a.m., Canlaon's seismic network records a sudden cluster of volcanic earthquakes, over 60 in a single morning. Within minutes, the monitoring dashboard flashes red, data feeds from Negros Island spiking with ground shaking and gas emissions. By 6:47 a.m., Canlaon erupts, sending a plume more than 4 kilometers into the sky. FIVO-LCS upgrades the alert level to 3, and the message goes out. Evacuate 5 barangays, watch for lahar. Local government units are notified in less than 20 minutes. But Canlaon isn't alone. As engineers scramble to validate the readings, Bulusan's sensors in Sorsogon start showing a swarm of volcano-tectonic quakes, nearly 300 in 4 days. Steam and gas venting from the summit reach 400 meters high. The sulfur dioxide output jumps to more than 1,000 tons per day. Within a week, FIVO-LCS raises Bulusan's alert level as well, warning of possible sudden explosions. TAL's network, meanwhile, records a surge in tremors and gas flux. On May 3rd, the alert level quietly moves to 2. By the end of the month, all 3 volcanoes are on heightened watch. The command center's main screen now glows with overlapping warning banners, each color-coded for urgency. Data bandwidth strains under the load. Real-time seismic, gas, and satellite feeds pouring in from Luzon, Visayas, and Mindanao. Staff work in overlapping shifts, led by FIVO-LCS Director, Dr. Teresito Bacolcol, and Senior Volcanologist Ma Antonia Bornas. Each volcano has its own crisis team, but the lines between them blur as the signals multiply. Situation reports are drafted, revised, and pushed out to local officials and the National Disaster Risk Reduction and Management Council. Within hours, evacuation orders are issued in Negros, curfews declared, and flights diverted from ash-laden airspace around Iloilo. The Department of Health circulates air quality warnings as sulfur dioxide levels spike. Social media fills with conflicting advisories, tourism boards downplaying risk, local officials demanding clarity. FIVO-LCS issues 3 overlapping bulletins in 5 days, each one more urgent than the last. Amid the chaos, the command center's dashboard becomes the nerve center of the nation. Every spike in seismicity, every plume, every tremor is logged and relayed in real time. The sense of urgency is relentless. Inside the control room, experts debate evacuation radii, weigh the risk of false alarms, and field calls from anxious mayors and national leaders. The pressure is unyielding. One mistake could cost thousands of lives. As the alerts cascade from one volcano to the next, it's clear that the Philippines is facing an unprecedented threat, one that tests the limits of science, government, and the resilience of its people.